Hello, everyone. Today we have a joint seminar of two JetBrains Research laboratories, a Nuclear Physics Methods Laboratory and Cyber-Physical Systems Laboratory. And our talk for today is by Igor Khokhrikov from DAISY. He will talk about walls controls and our vision of distributed, lightweight, heterogeneous control systems. So please, Igor, feel free to start.
Yeah, thank you, Alexander, for introduction. But just to be sure on the agenda, because I also will talk about the TANGO controls in the beginning, and then switch to walls controls and how it's actually different from the TANGO controls or other solutions. Is that okay with you? Or?
Yes, it's perfectly fine.
Okay. Let me introduce myself. As I said, my name is Igor Khokhrikov, and basically there's some short information about me. I've been CTO for IK company since 2016, and I also work as a solution architect at Helmholtz Central Gate Station DAISY since 2011. I'm also a TANGO controls kernel developer between 2016 and 2020, and in roughly I have more than 10 publications related to TANGO and walls controls up to date. As I said, I would like to give a short introduction to the TANGO controls, and extremely short, basically a software that thinks people sitting here in the room to the hardware somewhere in structuring, and these are pictures taken from the SRFs for the source in Europe, Grenoble, France, where the TANGO controls were actually born. So then I think the best.
Igor, sorry. The quality of sound is terrible. Is it possible to reconnect? Maybe again.
Which microphone? And the
microphone. No, I think the microphone is okay. It seems like the problem is maybe switch microphone. No, not this one. Okay. Yes, here, and maybe switch settings and maybe switch microphone. Yes, to the different one.
You can also try maybe to adjust this volume here. Is it better now?
Yes, a bit better.
Fine.
Okay.
So
let's continue.
Sorry for the technical problems. Internet.
No, it's still bad. It's still bad. It's something with the bandwidth, I think, or the microphone itself. So it's.
So is it better now?
No.
Okay, then maybe I'll try the Bluetooth.
Maybe switch to different microphone.
But this should be much better than the built one.
Okay,
so
let's try.
Is it okay? Is it better?
Yes, much better.
Okay, perfect. So yes, back to the presentation. I just wanted to, well, maybe should we start from the beginning?
Okay, let's try, but I still hear some problems with the sound. Okay, let's go further.
Okay, so I just wanted to go to the TANGO controls website to give you a short feeling of what it is. And it basically offers to its users. Come on. Yes. Yes. So what is TANGO controls? It's basically a framework, a toolkit, a software toolkit for building and distributed control systems. So in a very low overview, it looks like this. So we have some kind of hardware, typically a synchrotron, because it's built in synchrotrons and used mostly by the synchrotrons all over the world. Then we have a driver to that hardware, some custom code, which we write ourselves. And then we have this TANGO ecosystem. So there is a bunch of applications, APIs, libraries, things like that, and they all talk within the so-called. Like other projects, this one is like Apex or DOOCS. This one is quite big, has a lot of contributors, but what is most importantly is that these contributors pay money. There is some kind of collaboration contract which is signed by each party here, and they contribute into the some fund which is then distributed to support the TANGO controls itself. So they hire like outsourcing developers, the technical writers, and so on and so forth. So for instance, this website is maintained from that money, and so something really completely different from other projects on the market. There are also regular events. Hopefully there will be an offline event this year in St. Petersburg, but we're not sure because of the stupid COVID. And so if we go to the community, there is a lot of stuff going on. So for instance, in the forum, it's quite active, like I know really all entries here, people asking and answering questions about TANGO and so on. There is also a lot of ecosystem, a very rich ecosystem for the developers. So there are core libraries, obviously, basically APIs, written in different languages, mainly 3, C++, Java, and Python. Then there are some core servers or services, access control, some monitoring, watchdogs, databases, and so on. Bindings to other languages and frameworks. A lot of tools already there to tune the TANGO controls, set up, create new services, and so on. Archiving, GUI frameworks, and a lot of frontends as well. And another interesting thing about TANGO controls is that they have so-called device catalog. So basically, this is a endpoint in already existing services for the hardware and maybe also some software systems like REST API, for instance. Or maybe if you have some hardware which measure temperatures, there is a lot of vendors here, and for those there are already some code written down, so you can take it and use it directly in your projects. And there is also very rich documentation, like thousands of pages, and covers almost any topic related to TANGO controls. So this is very well maintained. As I said, it's been outsourced to a third-party company which maintains the documentation, constantly updates it, keeps integrity of the indices, so you can easily find something here. So let's go back to the presentation. TANGO is not the only solution we have to deal with. For daily, I know at least 4 SCADA systems that are used simultaneously on a single campus. So these are basically TANGO controls, of course, TINE, DOOCS, Karabu, and there's also a lot of smaller scale projects. So there is a lot of different SCADA systems. There is a lot of different data storages. So people want to use, for instance, HD5 or some databases and so on and so forth. There's a lot of hardware which is not covered even in the TANGO controls. There is a lot of such things. And plus there is nowadays there is a lot of projects related to GUI optimizations and integrating with machine learning and artificial intelligence. And the problem is that all these systems have very different entry points, APIs, and so on. So if we try in a short way, it's very harmful, like in this short video. So basically, what controls about is that we want something like this. So very flat-lined and easy to use and operate system, which sits on top of all other entry points that I just mentioned. So this is an open source solution. The idea is that we have a magic component, so-called magic component in the very center, which is basically a reactive stream sorter. So every entry point or upstream system which are connected to this magic thing produces some kind of events which then packed into the messages and streamed around the whole infrastructure. And this way the different components may communicate with each other being totally decoupled. So GUI may not know anything about the upstream SCADA system or any hardware or data storage. It just attaches to the event stream and using standard reactive extensions deal with the events coming through that stream. So this is all built within this Piazza project, which aggregates the central component, the magics, and there is a bunch of connectors to the upstream. The controls are based on three main pillars, so to say. The first one is a GUI platform, the Piazza project, so as I said, where all these connectors are living, and the magics, which is basically an engine to create reactive stream from the upstream data source. So at a glance, we have a RFC in development, so that before starting any implementation of any component, we first write a specification where we define how this component should look like, which API it provides, and most importantly, which kind of messages it will provide, and the structure of the messages. So all other components then can rely on that specification and just interpret the messages being sent around. It's totally asynchronous. So all messages are just sent and around without any waiting. So it's completely non-blocking communication, and it's being designed as a reactive system, meaning so it's responsive, resilient, elastic, and message-driven. And of course, there is a web integration for free because we can build the whole system based on HTTP, for instance. So talking about the roadmap, currently we are working on the RFCs for the critical components. Some of them are already stabilized, but since we want to integrate more and more SCADA systems and other stuff, we need to write RFCs for that. We have a, so to say, experimental implementation of this Magic Greenbox based on HTTP second protocol and SSEM for sending messages, but in the future we would like to have it more or less pluggable depending on the requirements. So this router can be built on top of Kafka or reactive sockets, things like that. So message payload specification is almost done. The components, The whole system can be built on top of blockchain, so the security will be untouchable. And yeah, finally, some upstream control systems connectors. And we also plan to have our own lightweight device API built on Kotlin. So there will be a way to, for instance, if there are no driver within the existing systems that is being used at the facility, for instance, for TANGO or TINE, we can just easily integrate this hardware using our own device API. To give a short overview of the components of the voice control. So the first one, the voice GUI, which is basically a platform which allows us to, instead of having such a picture, this Jive tool from the TANGO controls, and it represents a piece of information that our beamline scientists want to see, for instance, during the commission. So these are basically models, and they want us in the position. So we decided is the whole thing with them on profiles, meaning the different perspectives of the same hardware information. So for instance, here we see that monochromator motors with its positions, and so then quickly switch between different tables, which represents the different aspects and different perspectives of the hardware they're using and commissioning at the time. Of course, it can build some nice graphs and images. So it's a pluggable architecture. It's built on top of JS NPM dependency management mechanism. The middleware is written in vanilla JavaScript 6, and there is only third-party dependencies, reactive extension, obviously, required by us. And it's deployed and used on a daily basis at our inlines. There is also proof that there can be easily integrated different components, even from different developers. So, for instance, our colleagues from the Nuclear Physics Methods Laboratory implemented a grid widget. So you can find it here and watch the corresponding video on YouTube. So how they did it. So it's completely shows how absolutely different stack of technology can be seamlessly integrated in one user space. So that's user feedback. I will, I think, send around afterwards, so you can read it through. And the next two components, I combine it in one shot because they are really highly related to each other. This is a Piazza project, plus Matrix, or in common terms, basically, it's an interaction platform. So the idea is that we have this Piazza platform with core component which communicates, which not even communicates, aggregates, it routes the event streams, reactive streams from the different data sources, being that a GUIs or some SCADA systems, or maybe even injected hardware and so on. It's this kind of installation. We have a GUI based on whiles. Then we have this reactive stream component. As I said, it's an experimental development stage using HTTP and C. We route messages, data from TANGO and TINE currently to our GUI, and plan also to integrate some machine learning techniques now as we are dealing with tomography. We would like to reduce received data filtering through machine learning and artificial intelligence, because not all the images we are getting are useful for the further reconstruction. So this system already. So we are collaborating with Axis Group at DAISY, who is building a new free-electron laser source at DAISY. And we've built a small system that controls the spectrometer for that laser source. So, as I said, it's built on the experimental matrix implementation. To communicate with the hardware, we used basically Python libraries and obviously a reactive extension to it. And the GUI is based on words. There are also an ongoing progress to implement and have a showcase for our lightweight device API based on Kotlin for this thing as well. And the whole stuff was already tested during the beam time in South Korea in November 2020. So collaborations, and I hope so this project will go on and live long, prosperous life. And basically that's it. So thank you. And if you have any questions, this is the right time to ask.
Okay, thank you very much. It was a very nice report. Sadly, the sound was not good, but I hope that everyone interested in that was able to discern the meaning of everything. So if there are questions, Igor, maybe you should switch off the translation of the screen, because maybe it will improve the quality of just click stop sharing. Oh, I can do it first. Okay, maybe it will improve the quality of sound. So are there any questions right now? Okay, Vladimir, question, please. Your question.
My question is about slide number 5, where you mentioned LabVIEW and so on, some integrated development environment. And what about IEC 61131.3? It's standard for PLC technology programming. Do you deal with the standard?
I'm sorry.
Did you deal? Oh, do you know about the standard? I mean that PLC is a base for industrial automation for big control system, and PLC solution is based on the IEC 61131.3 standard as programming language, kind of structured text and so on. Did you deal with it?
No, personally, I don't use it. I don't deal with any PLCs. But basically, you're asking about the TANGO controls ecosystem. Am I right?
No, it's not about TANGO system. It's my question is about standard solution for industrial automation, or maybe and PLC solution. It's actually very popular for any. Yeah.
I can answer this question. Its question is not about the control system. It's a question about actually what we call a device server. What Igor showed us is that there are those points where your control system connects to device. Those called controls device servers in all control systems. And these, what we are talking about, the communication between the PLC and the control system is handled exclusively by this device server. So I am pretty sure that there are designated device servers for different PLCs, both in TANGO and DOOCS, maybe in TINE as well. But it's not. It's a question of the structure of specific device server. Did I answer your question?
Oh, okay. But my question is about what kind of language.
No language here.
Yes, I see. And my question is about language. Do you plan to use? Do your system orients to QEs targets to use? What kind of language? Just C or maybe Java or maybe Python you mentioned in the slide. But what about language IEC 6.11.31.3 language? And it is language to describe complex control algorithms. And in industry automation, such big guys like Siemens, on ABB, on Rockwell Automation use this language and to create control systems. So my question is about language.
I think that in order to properly answer your question, we need to skip to my report. I'm not sure we can do it today. Maybe next time if we are going. I probably will answer your question, but the general answer is that no, control system does not implement the specific language to directly program your controllers or PLC. You operate with a higher level abstractions like properties of the device. And if you want to create a logic which is specific to the device you are communicating with, for example, to a specific PLC, you need to implement this logic on the side of the device server, which I'm going to talk about.
Yeah. Okay.
Okay. So if we have time today, I can give a short. My report is much shorter. I can answer a question probably. Do you have any other questions?
And my other questions is about graphical user interface. You mentioned Waltz graphical user interface. Would you like to enlighten it a bit more with the questions? What is Waltz graphical interface? Graphical user interface. What is it?
Yeah.
Okay, and what is comparing for classical user interface kind in touch, for example, and so on. What various kind of graphical user interface system we use in industrial automation. Thank you.
Well, first of all, the Waltz GUI is not an end application. It's a platform. So using it, you can build mostly anything you want. I just showed an examples which I built, for instance, for our beamline scientists at our facility. And there is also an example of graphical user interface to control the spectrometer. The idea is that we have a platform which is seamlessly integrated into our reactive-based system. Because as far as I know, so the main goal of this platform is to provide a developer with a very convenient tools to create graphical user interface based on the reactive streams.
Yeah. And okay, what is it comparing to, for example, Qt, or maybe, for example, comparing to LabVIEW, comparing to InTouch?
Well, first of all, it's a different stack of technology because Waltz GUI is the web-based and the Qt is mostly for the desktop. I know there is some web independent.
LabVIEW has web.
Qt is like a huge framework for building very sophisticated GUIs, and you can build your GUI, for instance, also with our system because C++ provides a reactive extension, so you can integrate that library into the Qt project, and then also communicate using this reactive communication transport layer, and build everything on the Qt if you want. So for instance, if you have a manpower for that, please go on. And in our case, we just wanted to have some very lightweight and easy to set up and very easy to develop things that we can do and in a manner of days or weeks.
Okay, thank you.
Okay, if Vladimir does not have any other questions, Konstantin, you also had a question?
Yes, can you hear me?
Yes.
Okay, Igor and Alexander, thank you very much for interesting report. I want to ask about some additional for TANGO ecosystems. It's called Sardana from ALBA, synchrotron radiation source. Can you briefly describe or estimate the place of this system in the TANGO stack technology? And another question, what technology basically use for acquisitions and control beamline in the Petra light source?
So concerning the ALBA and Sardana, what was your question exactly? So you're asking how much effort will it take you to integrate it in some fresh ecosystem? Or?
Well, as far as I know, it's based on the TANGO approach for control, and so what it's give, what's and as far as I know, it's very popular for using for beamline controls on light source.
Well, I doubt if it's popular. It's basically used at ALBA and DAISY, and EasterF is developing their own new system called Bliss to control the beamlines and the other using different approaches. But basically, the idea of the Sardana is that you have a kind of execution server. It's a TANGO server to which you pass Python macros, basically scripts, and then during the experiment you execute the scripts. Plus it gives you some GUI stuff like plotting, command line control, and things like that.
Mm-hmm. Okay, and can you briefly describe what approach is more popular in the DAISY for beamline controls and
there is no really simple answer to that, because every beamline is more or less doing their own stuff here. But generally, most of the beamlines are TANGO operated. So there is a dedicated group at DAISY who is responsible for supporting TANGO infrastructure for the beamlines. So if the institute doesn't have enough resources to maintain their own professionals to deal with TANGO, they can usually redirect these issues to this dedicated group at DAISY. And this group also provides Sardana support. So by default, the stack looks like this. So you have TINA for the storage ring. So if you want some values from the storage ring, you have to deal with TINA. The beamline hardware most of the time is operated by the TANGO controls. Some are using Caribou and some very few Epics. And concerning the experiments themselves, they're usually, so the default solution is Sardana. Previously it was online, now it's Sardana, but every beamline is free to choose and develop their own solution if they have to. So for instance, for our beamlines, first of all, we have resources for that, and secondly, for some historical reasons and some political reasons, we are maintaining our own solution.
Konstantin, sorry, I've muted your microphone because there was a lot of noise, but you can unmute yourself and.
Okay, thank you very much. It's enough for my understanding. Yes, thank you.
Okay. Then are there any other questions? I also can say that if you have any other question, please don't hesitate to ask. And if there is the discussion is interesting enough, we can then ask Igor to join one, for example, JetBrains Research Slack to discuss it in more detail. Right now, are there any questions to Igor? I don't see any questions. Okay, then we still have some time. So I would like to ask Vladimir if I should go with my short presentation about the device servers right now.
I think it's quite possible.
Okay.
Yes, please.
Yes, okay. I've made it quite short, but maybe it will answer some questions which were asked. Let me check. Aha, I've already turned it on, so there should. Moment, please. Yes, and now you should see my presentation if everything is okay.
Okay.
The project is now called Controls Kit, and the initial urge to develop it was before we met with Igor. I've started to working because with the experience on Troitsky mass experiment, and Troitsky search for first it was electron neutrino mass, now it's a sterile neutrino, and we found that you need to create a control system, not only the so-called slow control system, but the big data, fast data controls as well. And the problem is that no vendor creates a nice software, user-level software to interface with. So basically, people create drivers which are nice, low-level drivers, but the user-level software and the transport protocols and the storage are usually terrible. So you always need to recreate the user-level software from scratch, which is greatly time-consuming. And more importantly, the software from different vendors do not cooperate. They do not work together. So there is no clean way to make it work. I looked at this time, I looked at TANGO, but it seems to be a pretty complicated thing for a small experiment like ours. So what is the idea? What is a device server? The device server is a term from control systems. The device server is basically a program which communicates with the device. You hear device here, and you have device server. In my experience, all control system works in the same way. They do not have any complicated logic on the device server API abstraction layer. But instead, they have a number of properties which designate the state of the device. In TANGO, those properties are called attributes. They're a little bit confusion. In most other systems, they are called properties. So basically, when something is changed inside the device, it sends the signal and the property is changed. When you want to change something inside device, you send the signal via network or whatever, and it changes the state of the device. Also, usually they have something like a command, or it works the same way as the property does, but the difference is that it just executes some kind of action on the device. And those device servers could be pretty complicated. For example, they could include local storage, they could include synchronization of signals, they could include logging, etc., etc. DOOCS system used it at DAISY and sub experience at DAISY uses mandatory local storage. TANGO controls, I'm not sure. As far as I remember, it does not use mandatory storage, but Igor could clarify this point. Okay, this is basically how device server. So to answer a previous question from Vladimir, if you want to do some kind of logic inside your device, what you do is you create a property which handles this logic, and those protocols, PLC language, etc., they're handled by this device server and this communication. And the idea of the device server is to abstract away this communication. So the control system does not know in which language do you communicate with the device. The language in which to write this device server is another question, and we will discuss it. Basically, how it works with the network. I hope the picture is good enough. So you have those device properties. Here I already written what we devised a way to work with this controls kit and magics. So this is a modern idea. It's not exactly how, for example, DOOCS or TANGO works, but basically it's the same. You have properties, then you have some kind of external connector. It could be a message bus, like we propose in this Waltz, Magics, Piazza. I'm a little bit confused with the names, a lot of them. Or it could be synchronous communication, like it is done in DOOCS, for example, or like the primary mode of operation in TANGO controls. The TANGO controls nowadays have an additional mode of operation via 0MQ, which is, I don't remember how it's called. It's some kind of message streams. But still, the primary mode is the synchronous mode, when you send the request and get response synchronously. So your block sender when it's sent. And there is some kind of device manager which sets up the new devices from some configuration database, like it is done in TANGO, or some local configuration like it is done, for example, in DOOCS. And the idea is why they do control systems is that they do it in order to access the properties of the remote device as if it is near you. So you are basically, it's a very simplified form of a remote process call. What problems are there? The main problem, as I mentioned before, is it should be easy to create a device server, because you have tons of different device servers from different vendors. So you need, it should be easy to create this wrapper and operate with it. And even a guy without a lot of programming experience should be able to do that. It's not the case, neither for DOOCS nor for TANGO, and for EPICs and systems like Siemens, it's even more complicated. So it's a problem. We need some kind of API to make this task easier. The second problem is that you usually want your device to run in standalone mode. So you want to test it. You want to work with it without attaching it to the huge control systems. And again, it's a problem for all large systems, because you need to create a lot of facilities to make it work. The storage data database, the configurational database, the specific name resolving service, etc. We need a more or less common protocol to communicate, because devices from different sorts of vendors should be compatible. We can't always rely on the same vendor for that. And the problem with the existing systems, like, for example, TANGO uses Corba, and DOOCS uses Sun ONC, that they all use different, and the EPICS uses its own protocol. The problem is that we need some kind of common ground for communication between these devices. And it should be as simple as it could, because otherwise we won't be able to make it universal. And finally, I showed in this when we have this synchronous request, like it is in most of modern systems, there is a problem with scalability. Our partners at, for example, at Tavrida Electric, an industrial company, they already have this problem. If you have a lot of changes, a lot of requests, then each blocking call is a problem, because it could cause you a loss of time and deadlocks and a lot of different problems. So the synchronous communication is basically a problem. We can probably make additional seminar about the synchronous calls and asynchronous calls and why it is the problem. So now what we propose to solve those things on the device server level. First of all, we need to remember that there are two different layers of properties, actually. We have a physical layer, which is a real physical state of the device you are working with, and there is a logical layer. Why we need two separate layers? Because we do not want to re-evaluate physical state each time we request property. For example, you have some kind of sensor which changes its value like once per minute, and you need to make 100 requests per minute to this device. But the request itself is pretty expensive, because it's you need to pass this command. So in general, you should just store the current value of physical property and respond with the current value and update it only when something is changed. So if your device supports asynchronous update, then it just updates your logical device and sends the event to remote. This is, in here, I mean asynchronous message passing loop. An additional second way is a timed update, when you have some kind of external clock or internal clock or some scheduler which says just update the logical state each, I don't know, 5 seconds. And then it works like this. It starts the update, gets a response, and then, oops, what happens? Sorry, I'm not sure what happened. Do you see my presentation right now?
Yep.
Yes.
Yes. Sorry, something broken. Go back, please. And then it sends the update if it is changed. So you can save a lot of traffic here by sending only changed state. And the final way, it's requested updates. You can force the value to be updated and send back the event. What is important here, which is a difference, for example, with how most of modern control systems operate, the update is asynchronous. So when someone sends a request, it does not blocks and waits for the response. It just listens to update events. Second problem is a data format, and currently most of the control systems handle it in the schema-based way, when you have some kind of schema and you serialize your state of your properties in some standard binary format, like, for example, Corba uses its own format, of course. DOOCS uses sign on AC, which also have some kind of format, and Apex has its own format. They are different, but for all of them, you have some kind of schema. The idea is that schema allows you to keep the type safety in a compile time. Compact serialization, it's because it's binary, it requires less space and less traffic to pass the values. Fast parse time, because numbers are in binary format. But on the other hand, one device must know about the other one in compile time to get all the benefits. So you need to know all the schemas in the compile time to get this type safety and all the other things, which is almost never is possible. in the control system, because one device does not know how the other device works, or you only know what property does expect. So it is a problem here, and I'm not sure that it is possible to know all your control system in compile time and make it work. And of course, different binary protocols are incompatible. What we're working on now is a tree-based representation, like for example JSON. JSON is a typical way of tree-like value representation. You do not have any specific schema. You can of course have validators for it, but you do not have schema. You just have a tree of values that you can interpret on the client side. Of course, it does not provide strong safety, but on the other hand, it provides a flexibility, and I think it is a good way to go. Current experience shows that it is a proper way of doing things, and there are also additional benefits. For example, you can automatically make algorithms which work on any type of tree. You do not need to specialize it for any specific scheme, and there are a lot of additional bonuses from the software engineering point of view. So how does it work? For example, here we have some kind of code. It's written in Kotlin, and the Kotlin has some additional benefits. I will talk about it later. Other benefits then it is developed by JetBrains, of course. And here we have a demonstration device which has a number of properties. It has a timescale property, which is a virtual property. It does not correspond here to any real device. It's a demonstration after all, but from the outside, it looks like a real device. And we can modify it from inside the program, or we can modify it directly from the network. For example, by sending it some kind of magic message. It has a time scale, a scene scale, and the scene is a number, not number, but the name of the property which you can read. So here this device has a property named sign, and you can read it. And in any specific moment, it will give you the result. And the same way it goes for cosine, and there is a composite property here, which consists not by one number, but the tree of free named numbers here. And actually, this is the whole description of the device. This is the whole program controlling the device. If you want, you can replace the body here by request to the network, or request to your USB device, or request to RS485 device, or whatever. But basically, this is how you do. And what is important here is that we can also set a schedule to update, to reread the properties and send them to device. If you go to the controls kit repository, there is also an device server demo with a visualization, with a web visualization. It should work. Of course, it's deep in development mode, but it should work right now, out of the box. Now, I'm probably will skip it. It's just a scheme we use we plan to use to work with the IAXO experiment to integrate with the existing DOOCS systems. The idea is that we do not want to create a new standalone control system which will replace DOOCS or TANGO or whatever. We want to just implement simple systems which could be connected to existing control systems and integrated into them, and simplify the process of attaching external devices like the detector here, or services like UI, for example, walls here. Okay, I will skip it. The last problem, I'm not sure I should spend a lot of time here, but one of the problems we have with this task is that we need to connect the synchronous world to asynchronous world, because most of model control systems are synchronous. So it means that they just call something and they are waiting for response. And the system we are talking about right now is, I mean, the message passing is asynchronous. But of course, there is a way to do that. You can create those connectors. It's not hard. It's just everyday software engineering work. I'm bringing everything to the conclusion. So we have a common problem in science, engineering, and actually in such new areas like Internet of Things, like robotics. We need a flexible way to create those device servers. I mean, the programs which connect some external user to the device. And it should be as open as possible, because we need to make them interchangeable. We can't create everything from scratch. So what we need are the connectors to existing frameworks, to existing whatever. Current prototype, Controls Kit, uses Kotlin features to solve those problems. What features do we use? We use a very concise syntax. As you can probably see here, it allows a lot of freedom, and it allows us to make very compact device definitions, comparing to C++ or even Python. We use Kotlin multi-platform. As you probably know, Kotlin is a multi-platform language with a Kotlin JVM flavor, which is primary, but there is also Kotlin JS and Kotlin native, which allow us in future. Kotlin JS already allows us to create nice interaction components, standalone, simple visualization tools in the standalone mode, or maybe create plugins for walls. And Kotlin native will in future allow us to easily integrate with the native solutions written in C, or even work with the embedded technology, because we did not talk about embedded right now, but it is possible to do it as well. Yeah, already said that. So I try to keep it short, so we can still have some kind of discussion. So please ask questions if you have any. Yeah, Are there any questions? Some hand here. Okay, Denis, you was the first.
Yeah, hello. Do I need to switch on camera, or the audio is okay?
Yes, yeah, it's okay.
Okay, I've got a question and a note or comment on your report. Let's start with the question. Why Kotlin? And I will be specific on my question, because the answer could be quite wide. I'll try to narrow the scope. Why not C#? Why not D? Or why not some custom language which could be easily implemented via JetBrains MPS or Untitled?
Okay, the answer about C# or Kotlin is a little bit vague question, because the capabilities are very similar, and C# until recently was vendor locked on Windows. Right now we have a .NET Core, which allows us to work on different systems, but still the ecosystem is not, the scientific ecosystem at C# is not as large as a Java ecosystem, I mean JVM. So basically you can do it in C#, yes, and you can do it at CLR and .NET ecosystem. They have quite similar capabilities with the JVM ecosystem, but we decided to use it. It's more broadly used in this area. The D or other less known or even custom language, it defines the purpose, because we want to create a system which is will be flexible on one hand. It will allow us to do everything, and custom language won't allow you the flexibility, because you will, each time you need to add new feature, you will have to ask developers to add new feature. And on the other hand, we want it to be simple to teach and simple to use. If you use some kind of a rarely used language, like, I don't know, NIM, for example. NIM is a known language, but it's not very frequent. It will be a problem because you will have a problem with libraries. If you need a specific protocol, for example, or access to specific transformations. And in the same time, you will have problems with teaching people to use it, because it's not widely known. Did I answer?
Okay, thank you. And before a note, I want to ask you, am I right that your target audience, one of the goals of this project is to allow non-programmers to create these device servers, yes?
Not quite. The problem is that for non-programmers, there is a LabVIEW. We can't compare to LabVIEW in this way, because LabVIEW is a visual instrument. We don't want to replicate LabVIEW here. Basically, it's the idea to create for programmers, but for programmers with limited experience in the field. I can say that. So if you want to create something very simple for non-programmers, you should go with LabVIEW or similar solution, of course. But if you want to create something which is simple to maintain, I think the maintenance is a key point, because the maintenance on things like TANGO or DOOCS is a complicated thing and requires a lot of experience. In this case, I think that we are targeting people which are familiar with the programming, but do not have time to dive deep into the specific system design.
Well, I would add on that, if I may. Currently, the idea is that we hide all the complexity of the all upstream system. And basically, the client deals only with this reactive extension. So you grab a library, RxJS, RxC++, RxJava, whatever, and then basically RxPython, for instance. There is a lot of scientists who know Python more or less, and then they only need to understand a little bit this reactive extension, and then they will be already quite efficient in communicating with the whole system without knowing all the details, for instance, of TANGO or DOOCS or whatever they use. They just receive the messages, react on them, and send back the response.
Yes, it's a very good addition, because what we showed you is a prototype. We use Kotlin because it's easier to do, but Igor already implemented the similar design using, for example, Python. So if you do not like Kotlin, you can use the protocols to design this device server on any language you want. For now, we use Kotlin because the prototype looks quite good in it, but it is easy. It is simple to create a device server following the same protocol in another language.
Okay, and I see. And a note was the next one. I wanted to share my experience with such kind of tasks. I saw such efforts in game development. It's a common task in game development to give to designers or game designers a way to script somehow a game. So it's a common task to give unexperienced or less experienced with programming people some tool set to customize somehow the game. And I saw such efforts in computer-aided design. Right now, we are working with computer-aided design in the field of garment and clothing, and there was such effort in our company. Also, it's a common task to try to offload such programming tasks from professional programmers to testers to automate some testing in software engineering. And I saw all this stuff, and actually maybe I was unlucky, but every time such effort actually was a fail. In game development and in computer-aided design, in testing, when you are trying to give programming instrument to non-professional programmer with few experience, without programming experience, the code produced by these persons is always unsupportable mess. It's write once unsupportable code, and in several cases it had an impact on business. It impacted the money flow actually, and the whole architecture had to be refactored because of such decisions. And for example, maybe you know such game development company, Epic, Unreal Tournament, Fortnite, and they abandoned this idea all in their engine, or all the stuff that is done by non-programmers. It's visual via GUI without any scripting. Yeah, good luck, you guys. If you will manage to.
You understood me wrongly. You understood me wrongly because maybe I should repeat myself. It is not the aim to provide a script which could be run instead of device. Exactly. I think it's a bad way. And what you were talking about before, like the execute Python script somewhere in control system, I think it's a very bad solution. And I understand what's the problem with the scripting again. In this case, we are talking about programmers, but you need to understand I'm not sure if you had any experience with such as industrial control system. The problem is you not need to only be programmer, but you need in order to work with it, you need to have a lot of experience with a specific system. For example, if you want to understand something in TANGO, for example, you need to spend at least a month digging deep. Even with, for example, myself, I have more than 10 years of experience in Java and other language, but still I had to spend like a month to understand how it works. And the system we are doing is not for non-programmers. It's for programmers, but it's for programmers to make it without digging deeper in the details, how the communication between nodes works.
So your target auditory is not junior programmers, it's common programmers who have no experience with the system.
Specific system, yeah. So people can write their own code without thinking about how it works inside the system. Currently, it's not possible to do that in TANGO or DOOCS or Epic's even.
Oh, okay. Now it totally makes sense because Kotlin have a lot of features, and in game development, there were experiments with giving scripts, and it was a bad idea to give people such heavy instrument like Kotlin.
No, we are not.
So they try to reduce as much as possible language possibilities, but okay.
The basic idea is that the new guy comes. It's a usual situation. The new guy comes to the experiment, and he wants to read the code. He wants to understand how this program communicates with a specific device. In most of existing systems, you need to spend months understanding how the build process works, how the integration works, how the name server works, how the database works. We want to remove all that. And more importantly, we have, I personally, it's not Igor, it's myself, I work on the small experiments. And we also have target the small setups where you work not with hundreds or thousands of devices, but you work with like 5 devices. And you do not want to set up the complicated thing. You want to take only simple modules to work with a specific device. Okay, with a lot of time, I believe that Vladimir also had a question, if he still has it.
But my question is mostly about the same things. I'm interested in what is the advantage of the solution proposed, the proposed solution comparing to the conventional approach from industrial automation fields, kind of OPC, for example. It's open platform communication, consortium, a set of standards, and so on.
The OPC we're discussing with industrial people, yes, but OPC is only one of protocols communicating with one specific device. In order to do that, you need to understand deeply how this device works and how. But if, for example, if you want to connect it to another device which does not use OPC standard, OPC UA, I mean. It gets complicated. So there are different ideas here. The first idea, which Igor, I hope, translated, is that we want a common ground, a common API, which allows different systems to talk to each other. And as additional bonus, we have some things like web visualization. The thing I was talking about is a little bit different. It's a problem not when you have a device compatible with the OPC, but when you have completely new device with a completely new protocol. You do not have a LabVIEW drivers for it. You do not have DOOCS drivers for it. You do not have TANGO drivers for it, but you still need to connect it to your control system. That's where what I'm working on takes place.
Okay, thank you, and thank you for your nice talk and nice presentation. And also, my question is about what about we are speaking about control system constantly, but modern control system is maybe much more than just control algorithms. There is a security questions for various spacing, maybe climate control, and so on and so on.
Exactly. I think, yes, the control system is a bad term because people understand it wrongly. We are not talking about control systems. We are talking about controls APIs, I think, and protocols and communication protocols.
Yeah. Well, communication protocols. Okay. Thank you.
Alexei, you raised a hand.
Yeah, thank you for your great speech. I have a question about, for example, I'm working in Institute of Nuclear Physics, and we have a lot of devices.
I'm working there. I'm basically from INR, it's the Institute for Nuclear Research in Moscow. So yes,
yeah. I'm from Novosibirsk. So
yes,
the question is, we have a lot of devices that we are using. Just we buy it and then use some sort of DLLs that we implement in our system. How can I implement in your system new device if I have only DLL in C++ or C, or if I have like LabVIEW example how to use this device? How can I implement it with your
basically, if for DLL, Igor have an example which he showed. It's about those motors. They also provide a DLL-based driver, and he created a wrapper in Python on top of it, and it works perfectly fine. In Kotlin, it's a little bit more complicated, especially if you want to make it cross-platform. If you do not, you can just load a DLL as you load any library. I did not implement such examples right now. I did not have time, but we can work together and make a prototype for it. It should be quite easy.
Thank you. And about cross-platform, we use just one computer that works on Windows because most devices have only Windows drivers because of scientific issues. And
yes, my way of doing things, I try to recreate. I try to take raw protocols from the vendor and recreate the message passing in Kotlin, because usually they support TCP transport. So it's, in my opinion, it in most cases easier to recreate the protocol they use over TCP than to use DLL, because especially if you want to move this device between platforms, but it all depends on how much manpower do you have.
Absolutely agree. Thank you. And I have the second question. It's not about your speech, maybe, but it's a global one. In our lab, we have we have the facility that is working. It have like 3 stages: heating, like powering up, then working, and then like close working, like stopping our pumps or disable something. And we sometimes need some sort of algorithm how to like script algorithm. Do your system have something like this? And the question is, can physicists that don't know programming language really good, can they use it?
Okay, the question is, it's very similar to the one Vladimir asked at the beginning. It depends on which level do you want to implement this. There are 2 ways to do that. One way is to implement it directly in the device server. You can implement any logic there. You can even include what I've listened to talks by your laboratory. I mean, those about verification of different state machines, and you can implement it inside your device server, for example. It will be safe. The other way, if it is not local to the specific device, this is what Igor was talking about. We can create a microservice in our network. I mean, in our distributed, this heterogeneous distributed thing, we create a microservice. Igor was talking about artificial intelligence, but actually the external controller works exactly the same way. It receives the signal, and then it has its own logic. For example, it checks it, and it sends some kind of signal back to the this event loop. So you can make a service which provides a communication between different devices. I'm not sure we have time to discuss it in detail. It allows great flexibility, but of course there will be a question when there will be a lot of such microservices in the system which play different roles, if they will interfere with each other. So it's a good question. We will never know until we try.
Well, thank you. If it's possible, can you type your email? If I can, I will write it down. And also, if you have some sort of meetings like this, I'm really interested in it. So,
okay.
Thank you.
Okay.
Excuse me, Alexander, just we have run out of time, but maybe one short questions about do you think about safety of your protocol system,
yes,
of your algorithms? Or maybe some short answer.
Yes, if you look into the Waltz RFC repository, then you will see there is an issue I left there about the verification of user access rights. Currently, we do not have it. And I think I asked Igor, maybe you can answer yourself. Probably no industrial systems like DOOCS or TANGO have it just out of the box.
Well, there are some mechanisms, for instance, in TANGO, but it's very, very weak, I would say, in terms of security. It just checks whether the specific
about safety, not security, about safety, about various deadlocks or maybe kind of Mexican loops and so on.
If we are talking about deadlocks, then this should be avoided because we are using, if everyone, each part of the system has one input stream and one output stream. There are no locks inside. So if you do not create a deadlock inside your device, server, or your service, or your visualization service, it will work perfectly well. And if there is a deadlock on your device, it will lock only your device, not other devices in the system. So you do
yes, it's your just your words, but I speak about maybe a formal technique to prove this statement, maybe model checking, or maybe deductive verification, or maybe dynamic verification.
I can shortly answer that question.
What do you use?
We are using a reactive design, which is based on the 4 principles, so being resilient, responsive, elastic, and message-driven. And all these systems have these properties by design.
By design, okay. I see. I guess the answer.
Okay.
Of course, in any of your device server, you can do something nasty, and that will more or less crash everything. But at least in responsive systems, these are very isolated nodes. So if you crash something, it usually do not crash the whole system, and it stays responsive.
Yes.
In that matter.
Basically, we've spent the last week discussing nasty deadlock with the people from Tavrida Electric, and I think we found the solution. Yes, even if you are using reactive-driven approach, you can create a deadlock. But what is important here is that each participant of this communication process is more or less standalone. So you are sending events and you are receiving events. The only way you can create a deadlock if you inside a device you are waiting for some event. This should not happen if you do things properly. You should not wait for something. But if you do, of course, you can create deadlocks. In this case, you can apply all your techniques. I'm not specialist in here to verify the state of your specific device. You do not need to make a verification for the whole system because it basically does not have any global state. If I'm not sure if I am concise enough.
Okay, thank you.
Yeah. But of course, there are a lot of other problems which in asynchronous systems which we do not have. It basically microservices model. So microservices are very popular and they have a lot of benefits, but they have a lot of problems as well because each device does not know what other device does, and they all send messages. And as long as everyone adhere to this reactive paradigm, do not block anywhere and send messages only to those who need them, everything's okay. But of course, at some level, there will be problems because somebody will be sending wrong messages or will block something. And we will need, of course, to solve those problems as they go. But the benefit is that we can debug each device and each service separately. It's, of course, much simpler for maintenance.
So you couldn't guarantee that every messages you send must be received somewhere.
Yes, exactly.
Okay, and do you plan to guarantee this or no?
No, we do not. And basically, it's not because it will provide all the problems you're talking about. If you guarantee delivery, then you will have problems with the blocks, with the waitings, and a lot of other problems for synchronous systems. If we use, there are ways to mitigate the problem, understand the problem. There are ways to mitigate it. For example, Igor was talking about Kafka, industrial message delivery system, which at some level guarantees the delivery. It has some mechanism, internal mechanism inside the loop to guarantee the delivery. But if your device is dead, for example, it's just dropped out of the network, you can't guarantee it. We can use a Watchdog service, which regularly sends events, which checks the device is dead or not. But again, it's another level of complexity which could be done, but it's not on the guaranteed on the basic level.
Well, let's say that we are now already mixing the transport itself and the message flow, because all these guarantees are basically in the protocol in a way what messages are sending around and what responses are received. So, for instance, you can build such a system on top of the transport, and we are focusing on the transport, which doesn't guarantee anything but gives you a lot of flexibility to build different system for different cases, because if you embed such a guarantee, it's already a complication to your system, and in some cases you maybe not even need it, but it will be there will be bugs, and it's like a legacy you always have to deal with.
Yeah.
Okay, thank you.
Oh, maybe the last question from Alexei, because we are really out of time. We should we should make another seminar on this.
Oh, I have a really short question. If you describe your device in some sort of language, what status of the channel will be if the device is offline? For example, if device is online and you see some sort of like temperature is 35 degrees, and then the next time step, this device is dead. So what value will be on your system? It
depends on what when you see what. When you say that I am seeing something, then it means that you are talking about some kind of service which consumes the messages. And the behavior of the service will depend on what you wanted to do. For example, the world's controls components and the web, Igor said, they could, they're receiving messages. If they do not receive message in the time you allocated for that, it could provide null or non-value or missing value, or it can rise an error. It up to the developer who develops the system to make a correct interpretation of the data. You can also create a Watchdog service, which will send an event to each device with a regular time interval. And if it does not receive the response in the needed time, it will send the error message to the network. So when the device just dies out in the asynchronous communication, it does not produce any messages. You do not know that it is dead because it did not produce any error message. It just died. But the Watchdog service could produce a message and send it to your visualization system.
Okay, thank you very much. Thank you.
Okay, we should probably close for now because we are out of time.
And I would like to say a lot of thanks for this great conversation, and I am sure that our conversation will be continue in the future. Okay, thank you a lot.
Thank you. Bye, everyone.
Yeah, thank you.
Thank
Bye.
you. Bye.